Energetics 2, measuring energy changes. Calorimetry. Calorimetry. A few terms first of all. Heat. It's a type of energy transfer which occurs as a result of temperature differences. Temperature. It's a measure of the average kinetic energy of a substance. It doesn't depend on the amount of the substance. Enthalpy. A measure of the total energy of a substance. This does depend on the amount of a substance. Calculating the heat change of a substance. The heat change of a given substance when it's heated or cooled is related to its mass, its temperature change, and its specific heat capacity. Let's have a look at this equation. Q equals M times C times delta T. What does this mean? Well, Q is the heat change measured in joules. M is the mass in grams. C is the specific heat capacity. That's joules per grams per Kelvin. And that just tells us it's the energy required to raise the temperature of 1 gram of a substance by 1 Kelvin. And finally, we've got the temperature change. So that'll be the final temperature, subtract the initial temperature in Kelvin. But because it's temperature change, often it's given in Celsius, and it makes no difference it being change. Specific heat capacity values of some substances. So you see water 4.18, steam is 2. Obviously they're the same thing, just at different states. You've got copper 0.39, silver 0.23, sand 0.8, wood 1.7. So water is quite high compared to those other substances. When calculating heat change of a substance, a 50 centimeter cube sample of water at 20 degrees Celsius was heated to a temperature of 45 degrees Celsius. Calculate the heat absorbed by the water. Find the mass of the water first. We'll find the mass of the water first. It's quite straightforward. The density of water is 1 gram per centimeter cubed. So 1 centimeter cubed of water is 1 gram. So we just use density as a conversion factor. Okay, so if you've got 50 centimeter cubed of water, you can multiply by its density to get the mass of water. Okay, so 50 centimeter cubed of water is going to be 50 grams of water. Secondly, we'll find the heat change of water. We use our formula. So the heat change is going to be the mass, which we just calculated to be 50 grams up here. Stick that in. 4.18 joules per gram per Kelvin is a constant. And then we've got a change for 25 degrees because we've got initial was 20, final was 45. So that's a change of 25 degrees Kelvin. Do the math, 5225 joules, and put that to 3 significant figures. That's what we're given in the question. And do note again, the delta T values are the same using both Celsius and Kelvin, since it's a change in temperature. Calorimetry. Calorimetry is an experimental measurement of heat enthalpy change of a reaction. It's based on the principle of heat transfer. So you see here, you've got a spirit burner and it's burning some probably ethanol. The heat produced in this reaction is heating the surroundings here, which in this case would be water. And you call this the calorimeter. Calorimeter. And this would be the heat of combustion. How to find the heat of combustion? The heat of the system, which would be, I guess, the ethanol in this case, is equal to the change in the heat of surroundings, and that in this case would be the change in the heat of the water. Notice one is giving out energy, one is taking in energy. They're always going to be opposite of each other. One gives out heat, one is taking in the heat. So the heat of combustion is going to be equal to the change in heat of the water. Let's have a look. With exothermic reactions, we have the reaction taking place here, and you've got some water in a separate container above it. In an exothermic reaction, heat leaves the reaction, it's released, the water absorbs the heat, so the temperature of the water increases. Exothermic, the surroundings increase in temperature. For endothermic reactions, you've got the reaction absorbs heat, and it absorbs it from its surroundings. In this case, it would be the water in this container. And the temperature of the water will decrease. So the surroundings decrease, it's endothermic. What if the reaction is taking place in solution? It's taking place inside, in this instance, water. Water is a solvent. You've got, for exothermic reactions in solutions, reaction releases heat. The water here will absorb the heat. Then the temperature of the solution will increase. It's an exothermic reaction. It'll feel like it's getting hotter. Endothermic reactions in solutions, the reaction absorbs heat. So heat from the water goes into the reaction, and the temperature of solution decreases. So let's just recap. Reaction, exothermic reactions, heat goes from the reaction to the surroundings. Oh, I keep pressing that wrong button. Endothermic, heat from the surroundings goes into the reaction. The assumptions made for in calorimetry, and let's look for an exothermic reaction. The heat released by an exothermic reaction is completely transferred to the water. We have imagined that there's no heat loss. Also, that there's no heat transfer from the reaction to the reaction vessel, the calorimeter, or the thermometer, or indeed the surrounding air. So the heat transfer doesn't go in any of these things, isn't absorbed by any of these things. And finally, the specific heat capacity and density of a dilute solution is the same as water. So we treat these solutions as having a density of 1 gram per centimeter cubed, okay, and having a specific heat capacity of 4.18 joules per grams per Celsius. Here's a few images of calorimeters, which are just insulated devices to measure enthalpy changes. They might be, they might have air. You can see here, air is used as a, what's the word I'm looking for? Oh man. To insulate the inner container. So to try and prevent heat loss, then the heat exchanges will happen just within this inner container. You've got a stirrer, you've got a thermometer. Here we've got a styrofoam cup, and the styrofoam's a pretty good insulator. You've got an insulated cover too, you've got your stirrer and a thermometer, and the reaction will be taking place within, in this case it's probably water. And over here we've got some draft shields on the outside, stopping any airflow. We've got a insulating lid up here. We've got some a copper calorimeter, and you've got a burner here. So we're heating up, looking at the heat content of this, probably paraffin or something, here, and we're looking at we'll measure the temperature change of this water here. Okay, so this is the system, this is the surroundings. Example 1, enthalpy of combustion. A student uses a spirit burner containing ethanol and a similar calorimeter to find the enthalpy of combustion of ethanol. The data is recorded. We've got 200 centimeter cubes of water. We've got initial temperature change of 23.5, final is 36.5 degrees Celsius. Initial mass of the spirit burner is 187.88 grams, and the final mass of spirit burner is 187.43. And we want to calculate the enthalpy of combustion of ethanol. So we're going to look at the mass change of the stuff down here, and the temperature change is of the surroundings of the water here. Step 1, we need to calculate the mass, okay? The mass. And you can see here we've got 200 centimeter cubed of water, okay? And so that will give us, using density as a conversion factor, 2 times 10 to the 2 grams. We'll stick that in, we've got the mass of 2 times 10 to the 2. We know the specific heat capacity is 4.18, and we know the temperature change because it gives us over here 36.5 minus 23.5, and you can do the math and you get the heat change of the water. Now do notice that you're not putting in the mass change of this spirit here. Okay, we're calculating the heat change of the surroundings. Okay, you can be very careful with this. But once we've got the heat change of the surroundings, we know that the heat change of the reaction is just the opposite of that. So the heat change of the reaction is going to be the negative of this. So it's minus 10.9 kilojoules. Now we need to find the moles of the limiting reactant, which we can do. We know the grams involved at the beginning and the end, and we can use the molar mass of ethanol conversion factor to calculate how many moles were involved of the ethanol. Finally, to calculate the enthalpy change, we know that 0.00976 moles gives a enthalpy change of 10.9 kilojoules. If that gives a change of this, then 1 will give a change of 1.12 times 10 to the 3. We're just using ratios there. If this goes to this, then 1 goes to question mark. You can just stick an equal sign between them, stick lines underneath, and find for the missing value x. If you don't like doing things like that, you could of course put 1 mole multiplied by you're trying to find the 1 mole, so it would be 0.00976, etc. Over 10.9 kilojoules. That'd be moles, and you cancel the moles out, and you get the same answer. Okay, so either way you like to do it, you're going to get this same answer. The standard enthalpy of combustion of ethanol in table 13 of the chemistry data booklet is minus 1367 kilojoules per mole. Evaluate the experimentally determined value. So what's the percent error, in other words? Well, we know to calculate percent error is experimental value subtracted the actual value divided by the actual value times 100. Okay, so stick in the values and you'll get a percent. Note, the experimental value is less than the actual value. Remember that the meaning of the negative sign for delta H is simply that heat is released. In terms of the amount of heat released, you should only consider the magnitude of delta H values. Right, this change, you think it's going to be random or systematic? That's right. It's almost certainly going to be systematic because we are losing heat to the surroundings. You can't do an ideal experiment in reality, and heat will be lost into the thermometer, into the surroundings, etc. You might get a little bit of random error as well, but it'll be inconsequential compared to the systematic error, most probably. Example 2. Enthalpy change of an aqueous reaction. When a reaction occurs between a solid and a solution, or between two solutions, a simple coffee cup calorimeter may be used. The system is the chemicals dissolved in the solution. The surroundings is the water present in the solution. Okay. A known volume of silver nitrate was added to simple calorimeter. The initial temperature was measured, and then a known mass of zinc was added. The maximum temperature reached was recorded. Let's see what we're given. We've got a volume of a given concentration of silver nitrate. So we've got volume and concentration. We've got mass of zinc, which means we can work out moles of this, and we can work out moles of this, can't we? We've got the initial temperature of the solution and the final temperature of the solution. So, first thing, let's find the limiting reactant. To find the moles of zinc, we'll use the molar mass to find 0.00306, is conversion factor, the molar mass. And then to find the moles, we'd use the concentration multiplied by volume, and we've got 0.005. The ratio is 1 to 2. And so if we look at ratio of 1 to 2 here, this would actually have to be 0.0006 to be sufficient to totally react with this. So this is the limiting reactant. And we can see those ratios from the balanced equation that's given to us. So silver nitrate is the limiting reactant. Let's find the heat change of the solution. Well, we know we've got 50 centimeter cubed. It's the mass of 50 centimeter cubed of solution. We know we're going to use a density of 1 grams per centimeter cubed. We're going to treat it like water, so we've got 50 grams. Plug it into the formula. 50 grams multiplied by 418, which is the constant specific heat capacity of water, multiplied by the change in temperature, and we get our heat of solution, 940.5 joules. Finally, we're going to find the enthalpy change of this reaction. So if that was plus 940.5, we know that the heat of the reaction giving out this heat is going to be minus 940.5 joules. This is going to be the exothermic reaction producing this heat, which was absorbed by the solution. So we now know the joules given out for a particular amount of moles. Okay, we know that the heat of the reaction here, which is calculated, is for the particular moles of the limiting reaction. And if we want to find out what it is for 1 mole, you multiply it by the limiting reaction in the equation, the moles of the limiting reaction in the equation, which in this case was, we got 2 moles. Okay, so we've got minus 940.5 joules for 0.05 moles multiplied by the moles in the equation, and we get minus 376,200 joules, which gives us minus 3.8 times 10 to the 2 kilojoules with 2 sig figs. Example 3, this is interesting. You can make temperature corrections for slow reactions. Heat loss is unavoidable during every calorimetry experiment. The slower the reaction, the worse it gets, the greater the chance for heat loss. If temperature data is recorded throughout the experiment, it is possible to correct for that heat loss and use this method. So we've got temperature on the y-axis and we've got time going along the x-axis. Okay, you can see there's a gradual increase in temperature over a given time. And what you can do is, once you've done it, allow it to continue cooling down, and you're going to extrapolate this line backwards until you pass the point where it first started to increase. And then you can determine the final temperature as if the reaction were instantaneous, which would be at about, starting at 73. Okay, so it went from, I don't know what that is, 30, like 25 or something, up to 73. A neutralization reaction is carried out between 1 moles of decimeter cubed, 1 mole decimeter cubed of hydrochloric acid and 1.5 moles decimeter cubed of sodium hydroxide in a simple calorimeter. The following data is recorded. You've got 1 mole decimeter cubed of HCl, and you've got 80 centimeters cubed of it, and you've got 70 centimeters cubed of the NaOH. So we've got concentration, we've got volume. That means we can calculate moles for both of these, okay? Because all you need is concentration and volume to calculate moles, as we know. The initial temperature of sodium hydroxide, 21 degrees, initial temperature of HCl, 22, and the final temperature of solution goes to 33.8. So we're going to have to take an average initial temperature at some point here. We've got the equation. You can see it is a 1-to-1 ratio. If we calculate the moles of HCl using concentration multiplied by volume, we get 0.08, and the moles of sodium hydroxide, concentration multiplied by volume gives us 0.07. So obviously the sodium hydroxide is the limiting reactant. Let's find the heat change of the solution. Total volume solutions is 80 plus 70, so we've got 150 centimeters cubed. The density is grams per centimeter cubed of water, our conversion factor. So we've got 150 grams. And the average initial temperature is just an average of those two different temperatures given. So add them together, divide by 2, we get 21.5. Whoops. So we're going to find the heat change of the solution, put in the 150 grams, 4.18, and our final temperature multiplied by the average initial temperature to get the joules, the heat of the solution. To find the enthalpy of neutralization, the heat of the reaction is going to be the negative of whatever the heat of the solution is, and so just stick a minus in front of it. And then it's quite easy just to plug things in, because remember it's a 1-to-1 ratio, so the we can just put in the heat of reaction in this case divided by the moles involved, which is 0.07 for the sodium hydroxide. It gives us 1.1 times 10 to the 2 kilojoules. Okay, a good idea would be to go through that presentation again real quick and write down the key points on this sheet of paper relating to how you find enthalpy changes experimentally. Okay, make sure you understand each of the different things we went through there. Splendid. Goodbye.